In this video, we'll be looking at how the simple yet elegant wave equation pops out of the most bizarre of oscillations. At the end of the video, we will see an extension of the wave equation in 2 dimensions and 3 dimensions. I will not be giving proof of the same for the latter cases, but after understanding the wave equation in 1 dimension, the 2D and the 3D cases become rather intuitive. Let us start by exploring a string under tension. We assume that the linear mass density of the string is mu and it's under tension T. Sampling the forces in the x and y direction, we get that the net force along the x direction is 0. This is rather intuitive as there is no horizontal displacement of any matter, but we do have a net force along the y direction, and that is given by analyzing the forces using Newton's second law. We get that the net acceleration along the y direction in the string is given by this equation. Here delta x is the small segment of the string, which at our scale of observation is effectively a straight element. Now we need to find more about the delta theta quantity. Consider the tangent on that element delta x, which is given by this equation. The reason why I use the partial derivative is that theta varies with the change in y, and at any given value of time the acceleration along y embodies the variation along x. Taking the first derivative of the tangent relation, we see that the square of the secant times delta theta divided by delta x is equal to the second partial derivative of y with respect to x. On slipping the quantities delta x and secant squared theta over the right hand side, we get that delta theta is equal to the second partial derivative of y with respect to x times delta theta divided by secant squared theta. Now I want to emphasize the fact that theta is a small quantity in our calculation. You might think that that's because we want to simplify our calculations. Well, yes, but remember how we started for our string element, delta theta. Delta x is effectively a straight line, and therefore the assumption that theta is nearly 0 is good enough. This gives us a direct relation between delta theta and the variation in transverse displacement y. This brings us to this following equation. Plugging this delta theta in our force equation, we get that the second partial derivative of y with respect to time is equal to the tension divided by the linear mass density times the second partial derivative of y with respect to x. As you can see, the delta x's on both sides cancel out, and this gives us our wave equation for a string. The wave equation here is representing a stationary wave. In the next video, we will be analyzing a traveling wave. I want to emphasize the fact that the quantity t divided by mu in this equation has the exact same dimensions as velocity squared. And indeed, it is the velocity with which a wave propagates in a string that has linear mass density mu and is under a tension t. But exactly what is moving? There are no actual particles in the string that undergo longitudinal displacement. So what does the velocity term give us? It tells us how fast or slow a wave is moving, that is, what is the velocity of the phase that is moving throughout the string. We will get back to this in a later video where we talk about phase velocity and group velocity. Until then, try to find out what would be the possible solutions to this wave equation that we have discussed today. Those will come in handy in the next video where we discuss the wave equations for a traveling wave, which also translates to the same wave equation which we derived today. Until then, take care, have a great day, and I will see you in the next episode. Bye-bye.